so it is recording now. Okay, so in our previous lecture, which was last week, okay, we have discussed about the concept of equilibrium. So what are the characteristics of equilibrium, and how do we know whether the equilibrium has been established or not? Okay, so those are considered as the introduction of equilibrium. Okay, the concept of equilibrium. Okay, all right. So we have one checkpoint that we haven't discussed. Question 1, state the characteristic of a system at equilibrium. Okay, state the characteristic of a system at equilibrium. Okay, may I know the answer for this? How do we identify whether the system is already at equilibrium? Guys?
The pressure and color are constant.
Okay, so that will be if we have 4 characteristics, that will be the third and the fourth one. Okay, so the most important thing that we would go for would be for the equilibrium.
Concentration.
Okay, what about the concentration?
Remain unchanged.
Sorry? Remain
unchanged.
Remain unchanged. Okay, all right, so that yes, okay, at equilibrium, the concentration of apa?
Both reactant and product.
Yes. Okay, the concentration of reactant and product will remain unchanged, but not necessarily be the same. So that is one of the characteristic, one of I would say important characteristic of equilibrium. Okay, all right, and then that will be the first, and then secondly, how do we know that it is at equilibrium? What actually happened at equilibrium?
Rate of forward reaction are equal to rate of the reverse reaction.
Okay, very good. Okay, the rate of forward reaction is the same as the rate of reverse reaction. Okay, and because of that, okay, once that phase is established, or once the equilibrium has been established, okay, which the rate forward is equal to the rate reverse, the concentration of reactant and product will no longer change. Okay, will no longer change. So that is the relationship between rate and the concentration of reactant and product. Okay, so that two characteristic of equilibrium are, I would say, most prominent one lah, ataupun most important. Okay, right. Then you have to remember those two characteristics. Okay, so the rate forward of this will be the answer. Okay, so we have this in our previous slide. The rate forward reaction equals to the rate reverse, and concentration of reactant and product remain unchanged, but not necessarily be equal. That means there's no net change. Okay, let's say, for example, after 10 seconds, the concentration is 0.1, and then after 20 seconds, okay, the reaction still proceed. It's just that the concentration is no longer changing. So what can we say about that situation? So we could say that and then we have to check again lah. Okay, after 20 seconds, the concentration still remain the same. After 30 seconds, it is still the same. Okay, so we would say that the phase, the situation ataupun the reaction at that time has achieved equilibrium. Okay, equilibrium. This is another point that you can consider. Okay, equilibrium can be achieved either from the reactant or the product. Okay, it depends on whichever that is placed first in the reaction. whether we put in the reactant or we put in the product first. Okay, because it is a reversible reaction. The arrow, we have two arrows, the forward and also reverse. If we put in the what we call that, the product first, that means the reaction will proceed to the left. Dia akan pergi ke kiri dulu. Okay, and then after a while the reverse reaction ataupun the forward reaction will take place, and after a certain period of time the rate of forward and reverse will be the same, and that is what we call equilibrium has been established. Okay, alright, so that's why dia kata kita boleh achieve either from the reactant or the product. It depends on whatever is put first ataupun placed first in the reaction. Okay, so we are done with that one. Okay, moving on to 2.2 equilibrium constant. Okay, we are going to start the calculation later on, okay, involving equilibrium. All right, so these are the learning objectives. So we have 4 learning objectives for this subtopic. Okay, make sure that you are able to cover all of them. Okay, all right, so what is equilibrium constant? Okay, so equilibrium constant, or we could simplify as KC, capital K and then C. Constant means K lah. Okay, remember rate law last time in topic chemical kinetic. Okay, we have constant, rate constant. Okay, so we represent rate constant as K, remember, but small k. But for equilibrium constant, for topic 2, we are going to represent the constant as capital K. Okay, all right, so equilibrium constant, if it is measured in terms of concentration, that means it will be Kc. That means K, capital K, shows that it is an equilibrium constant. C means the calculation ataupun the measurement is made in terms of concentration. Because later on we have Kp as well. Then P stand for pressure. Okay, alright. So K stand for equilibrium constant. So kita nak differentiate with the one that we have learned in topic 1 last time. Okay, topic 1 kita pakai small k. Topic 2 we use capital K. Okay, alright. Equilibrium constant, which is Kc, is numerical value obtained from equilibrium concentration. It's a numerical value. That means we can calculate this value. Okay, we can calculate the value of Kc. So consider the generalized reaction at equilibrium. So this is the generalized equation. We have A, B, C to produce C plus D, and this equation, okay, is at equilibrium, okay, with one another. Because of this, the presence of this arrow. Okay, it is reversible. That means this reaction, after a while, it will reach a point that we call equilibrium. Okay, all right. So how do we write the equilibrium constant for this equation? Okay. All right. So the equilibrium expression for this reaction would be Kc is equal to, okay, concentration of product raised to a power of X over the concentration of reactant raised to a power of Y. Okay, so what are the product and what are the reactant? Okay, with respect to the equation that we have, okay, the product that we have C. Okay, so don't forget the bracket, and then raised to a power of C. Okay, C dekat sini yang small letter ni represent the coefficient. Saya nak tukar dia punya ni. Okay, how do I change the? Sekejap ya. Alah, dia tak boleh ni lah. Aduh, macam mana nak turunkan dia? Okay, nak tukar colour tak boleh lah. Sebab dia dekat bawah ni, dia including the taskbar kat bawah ni. Sepatutnya. Okay, alright, tak apa, small matter. Okay, let's just proceed. Okay, alright, so see, we have C, D, A, B divided by A and B. And the good thing is that we can obtain the kuasa ataupun the power ni from the coefficient of the balance equation. Okay, we can directly obtain those kuasa, okay, dia punya power dia tu from the balance equation. So A we will get from this one, B from this, okay, alright. Okay, so it's product over reactant. Okay, the concentration of products over the concentration of reactant raised to their power. Okay, alright, so Kc is temperature dependent. Okay, like I said last time, remember rate constant can only be affected by temperatures. Same goes to equilibrium constant. It can only be affected by temperature, not other factors such as concentration, catalyst, surface area. Those will not affect the value of Kc. The value of Kc will still remain the same as long as the temperature remain constant. Okay. All right, so always specify temperature when Kc is quoted, because why? When temperature is different, that means the Kc will be different. That's why every time when it involve Kc problem ataupun Kc question, the question need to specify the temperature. Okay, we want to know whether the Kc is constant ataupun is it varies because of the change in temperature. Okay, all right. Normally we would fix the temperature lah. Kita akan fix the temperature. So you have to calculate the value of Kc. Okay, all right. And then the concentration equilibrium. Okay, it means that the equilibrium constant of product and reactant. Okay, so please take note, guys, when you are calculating for Kc. Okay, so this is very, very important. When you are calculating for Kc, the concentration that you have here need to be at equilibrium. You have to make sure of that first. Okay, you cannot just simply take concentration to calculate Kc, because Kc means the constant at equilibrium. So when you want to insert the concentration into this formula, into product over reactant, you have to read the question carefully, make sure that it's mentioned that the C, D, A, B, C, concentration of D, A, and B, okay, those were taken at equilibrium. Kalau dia tak cakap, that means maybe not at equilibrium. So dia kena specify that the concentration are observed ataupun are recorded at equilibrium. Then only you can calculate for Kc. Okay, so this is very, very important. Don't just see, oh, you ada concentration given to you and then you simply calculate the Kc. No. Okay, you have to make sure that the concentration given, is it at equilibrium or not? Okay, so this is very important. Equilibrium concentration of product. This is supposed to be ada EQ dekat situ. So it should be at equilibrium. Okay, so boleh tambah lah dekat sini. Sebab ni concentration equilibrium. So we may tambah ya EQ. Okay. Right, okay. So you may be wondering how in the first place kita dapat this formula. Macam mana kita dapat this formula kan? Okay, let's look at the process. Okay, how at the end of the day we get the product over reactant of Kc. Okay, for Kc. Okay, consider this reaction. So we have N2O4 in gas state, okay, in equilibrium with 2 mole of NO2 in also gas state. Okay, remember kinetics last time? Okay, so we can write the rate law. Okay, we can write the rate law of this reaction. So for forward reaction, that means if the reaction going forward, that means dia akan produce NO2. Okay, bila dia pergi ke kanan, it will produce NO2. So how do we write the rate law for this one? Okay, how do we write the rate law for this one? For this forward reaction. So it can be written as this. Okay, it can be written as this. Betul tak? KF. F stand for forward. This is the rate constant. Okay, so this is the rate constant. N2O4 is the reactant. Okay, raised to a power of 1. And as for the reverse reaction, okay, imagine, okay, if this reaction is going to the left, okay, so NO2 will be the reactant. Okay, dia akan jadi reactant. Dia akan digunakan dululah, maksudnya sebab dia the only one yang present pada ketika tu, that means it will be consumed to produce N2O4. Okay, so this is the reverse reaction, NO2 producing N2O4. So how do we write the rate law for this one? For this reaction, so rate is equal to KR, R stand for reverse, because actually this is a reverse reaction. Okay, if we are referring to the original equation, this is actually a reverse reaction. Okay, times concentration of NO2 raised to the power of 2. Okay, so this is the rate law for forward and reverse. Okay, remember at equilibrium, okay, the characteristic of equilibrium is when rate forward is the same as rate reverse. Okay, so just now kita dah ada the rate law kan, so we have this represent at equilibrium, so we just rearrange the rate just now can be transformed into this is for rate forward and this is for rate reverse. Betul tak? Okay, and then kita rewrite ataupun rearrange everything. Okay, kita transfer to one side for the constant and transfer to the other side for the concentration. Okay, so kita dapat this one. We got this. Okay, so again kita simplify. Okay, the ratio of the rate constant is a constant at that temperature and the expression becomes, so Kf and Kr, so these two are actually constant, betul tak? These two are actually constant. So we can simplify this into a constant, another constant that is known as K equilibrium. Okay, K equilibrium. K equilibrium is also known as, since we are measuring the unit used is concentration, ataupun kita measure in terms of concentration kan, so EQ means equilibrium. Equilibrium can be measured in terms of pressure and it can also be measured in terms of concentration. Okay, so when we specify Kc, that means we are measuring in terms of concentration. So Kc is equal to this, product over reactant. Okay, and don't forget the power. Okay, depends on the formula from the balance equation, the coefficient that we can get from the balance equation. Okay, all right. Okay, so that is for Kc. So if we have Kp, like I said, Kp, P stand for pressure. Okay, so Kp is only applicable for gaseous system. Okay, system that has gas in it. If we don't have gas, that means we don't have gas at all in the, reaction at all. That means we cannot calculate Kp because Kp, P, okay, pressure, okay, normally is measured for gaseous system. Ada je satu gas, katakanlah the rest solid and then we have aqueous and then we have gas, one product that is in gas phase. Yes, we can still measure Kp. But if any of the reactant or products are not in gas phase, that means we cannot calculate Kp. Okay, tak boleh calculate Kp. Okay, alright. So imagine that we have a gaseous system. The concentration of a gas in a mixture is proportional to its partial pressure. Okay, remember PV and RT last time? It is directly proportional. Okay, when we transfer P, okay, N, RT, so this is V. N over V, we know that N over V is equal to concentration. Remember? RT. Ni, N over V kan sama dengan molarity. Okay, concentration RT. So when P increases, concentration also increases and vice versa. So that is what it meant by is proportional to its partial pressure. Okay, so this is, let's say this is the, let's consider this equation, this general equation. So as you can see, like I said, we have gas. Okay, so for this case, for this reaction, all of the reactant and product are in gas phase. Like, maksudnya kita boleh calculate the KP lah. Okay, and also KC. KC is not a problem. KP ni dia applicable for gas system. Okay, right. KP is the equilibrium constant expressed in terms of partial pressure. The equilibrium expression can also be written as this. So you're gonna use KP instead of KC, and the concentration, the bracket, the square bracket will not be used. Instead, we are going to be using the P. Okay, sama juga. It is product over reactant. It's just that you are no longer using the square bracket, but you have to use P. Okay, kena guna P. Jangan buat begini C apa benda ni? Okay, don't do this. Ni apa? So you have to have P. This is for C. Okay, and then raised to a power of C. So this one we can get from the equation. Okay, and then times partial pressure for D. Okay, raised to a power of D. This one also you can get from the balance equation over reactant A and B. Partial pressure for A, partial pressure for B, and both are raised to their own power that we can get from the coefficient of the balance equation. Okay, alright. Tapi basically sama je. It's just that for KP we use partial pressure, KC we use concentration. Okay, moving on. Unit, equilibrium constant and unit, guys. Okay, does equilibrium constant has unit? Itu the most important thing, especially pada saya. Kita kena tahu whether it has unit or not. Okay, alright. So actually, equilibrium constant does not have unit. Dia tak ada unit. It is unitless, which is good lah. Good news for you guys lah, kan? Okay, when you are calculating for KC or KP, okay, you do not have to consider the unit. That means you only have the value, the numerical value at the end. Okay, alright. So let's look at why. Kenapa equilibrium constant does not have unit? Okay, alright. In thermodynamics. Okay, in thermodynamics, the equilibrium constants are defined as activities rather than concentration. Sebenarnya, the equilibrium constants, okay, they are defined in terms of activities, not concentration, okay, rather than concentration. Okay, so for an ideal system, what is activity? Activity tu apa pula? Okay, how do we measure activity? Okay, activity or apa, we can represent it as capital A of a substance, okay, is a ratio of its concentration, ataupun we can, other than concentration, we can also use partial pressure, okay, to a standard value which is 1 molar or 1 ATM. So activity adalah ini, concentration, okay, over concentration reference, macam tu, which usually would be 1 molar. Ini maksudnya activity, concentration yang kita measure tu over the concentration of reference. So that is what we call activities. Okay, so this is in terms of concentration. Kalau in terms of pressure, activity, okay, P over P reference or 1 ATM. Okay, so it's a ratio. The ratio of its concentration or partial pressure to a standard value which is 1 molar or 1 ATM. So this procedure eliminates all unit but does not, okay, so we will look at this statement after this. Okay, it will eliminate all unit but does not alter the numerical parts of the concentration or pressure. Okay, so that's why it's KC ends up with no unit, because it cancels out the unit, but not the value too will still remain the same lah. It's just that the unit will be cancelled out. Okay, consider this general equation. Okay, if we were to write KC in terms of activities, Okay, macam thermodynamic ni, in thermodynamic sebenarnya instead of using concentration, we use activities to describe. Katakanlah, okay, kita write the KC in terms of activities. So this is how the KC should be written in terms of activities. Okay, alright. So bila kita kembangkan, dia sama je product over reactant raised to their power. Okay, alright. So bila kita kembangkan activities tu, kita akan dapat begini. Betul tak? Concentration of the C divided by concentration reference for the C jugalah, for C. Times concentration for D divided by concentration of reference for D. Okay, which I mean semuanya pun 1 molar lah. For concentration reference you will get, it will be 1 molar. Okay, divided by reactants. Okay, alright. So what you get here is that bila you transform this one in terms of unit, okay, in terms of unit. So atas unit dia mol per liter, betul tak? Bawah pun mol per liter, molar. Okay, so they will be cancel out. Sebelum kita selesaikan dia punya power lagi, it will be cancel out. Dia boleh di-cancelkan. Same goes to this one, this one, this one, this one. So you end up dengan value saja without the unit. So that is why KC and KP are unitless. Okay, are unitless. Because we are referring to activities. So to simplify, maksudnya after all, the concentration of the reference concentration is always 1 molar kan. Okay, so dia always 1 molar. It will not affect the value. It will not affect the numerical value. Kata kita kena bahagi kan later kan. It will not affect the value because the value will always be 1. Okay. It's just that unit sekarang ni bila kita simplify kan dekat situ, dia cancel out. Okay. So that's why we might as well just use the concentration sahaja. Tak perlu cari activities. Okay. To simplify things, we use concentration. Okay, sebab concentration tu bila dibahagi dengan 1, dia tetap akan dapat the value of concentration. Faham tak? That's why instead of using activities, we can use concentration. Okay, sebab dia kalau activities dia kena divide by 1 molar. 1, which is 1 molar. So 1 tu kan any value you divide dengan 1, you akan tetap dapat the same value, the numerical values kan. So, tak perlulah kita nak menggunakan activities, okay, formula activity. Instead, we can directly take the value ataupun use the value of concentration. Okay, so that is why KC and KP are unitless. Okay, so this is for KC lah, but it's the same explanation, the same understanding for KP. Okay, it's just that it will be ATM lah. ATM. Okay, so you cancel out. Macam ini. Exactly as this one that we have here. Okay, alright. So standard value means reference. Okay, reference. Moving on, any question related to KC? Guys, so far, how are you guys doing?
No, madam. Okay, so far so good.
Alright, okay. Thank you for the response. How about others?
Okay, madam.
Okay.
Okay, alright.
Okay, madam.
Okay, faham Okay, itu baru intro. Lama betul intro kita. Okay, tak apa. Itu baru nak intro kepada KC. Okay, dia punya calculation part will be later lah. Okay, alright. So this is just an introduction to equilibrium constant. Okay, so we have K equilibrium. K equilibrium can be divided into KC and KP. C is stand for concentration. P is stand for pressure. Okay, alright. So now we have 2 types of equilibrium. We have homogeneous. That means later on we will have heterogeneous equilibrium. Okay, alright. So equilibrium constant expression for homogeneous reaction. That means all reactant and product are in the same phase. Okay, look at this example of reaction. So bila dia kata homogeneous equilibrium, okay, that means you have a reversible reaction and then all all of the reactant and product are in the same phase. Okay, therefore you can calculate for you can determine the Kc. You can write the Kc expression. Okay, soalan boleh tanya, usually the question will ask in terms of write the Kc expression. Ni, equilibrium constant expression. First, before you could calculate the value for Kc, you must be able to write, okay, the expression for Kc. This is what we call Kc expression. How do you express the Kc? So the Kc will be expressed in terms of concentration of product over concentration of reactant raised to their power. Okay, alright. It's just that ni dia nak tunjuk that kalau dia gas, kita hanya consider gas dengan aqueous je kan, solid, sebab solid we don't have concentration. Okay, concentration dia fixed. Okay, so bila kita calculate for Kc, kita kena determine, okay, kalau Kc in terms of concentration, kalau dia dalam gas, dia ada concentration tak? Yes, nitrogen, we do have concentration for nitrogen, hydrogen, we can calculate lah, we can determine the concentration. Same goes to ammonia. How about Kp? Okay, of course, sebab all of them are gas. Okay, all of them are gases. So, sama, exactly the same, it's just that the apa nama tu, instead of we measure in terms of concentration, now we measure in terms of partial pressure. Okay, so this is homogeneous, and heterogeneous will be, that means a mixture lah, a mixture of phase. Okay, that means more than one phase exists in reaction mixture. Example, okay, look at this first example. Sodium hydrogen carbonate, okay, in equilibrium atau reversible reaction producing sodium carbonate, which is solid, produce H2O also, and this reaction also produce, this is like decomposition of sodium hydrogen carbonate lah, okay, and also CO2. So kita ada mixture of solid and gas guys tu. So how do we write the Kc? The Kc is still the same, okay, product over reactant. It's just that bila dia solid, you kena be careful, okay, because solid will not be present in the Kc, because like I said, concentration of solid is actually constant. Dia constant sebenarnya, it will not change. Okay, alright. So as you can see, Kc, how do we write Kc? Okay. So sebenarnya kalau kita start from the beginning, kan, kita akan dapat begini. Sodium, kita buat produk dululah, okay. Okay, concentration kan. Okay, H2O, CO2. Supposedly kan, product over reactant. But you have to identify ada tak solid. So bila kita identify solid, that means kita assume that the concentration is constant. Constant bukan kosong tau. Kita boleh assume that it is equal to 1. So throughout the reaction it will be constant. Constant, so ni kita nak represent the constant. Okay, it's either the value is given to us ataupun kita boleh assume that it's just equal to 1. Dia berubah. Okay. Alright, so this one will not be added. So ni satu. So sebenarnya satu tak payah tunjuk lah. That's why you end up with this one. Okay, kalau dia tak boleh kosong. Kalau you kosong kat sini, you dapat apa? Infinity ni, tak boleh. Okay, so dia sebenarnya, the concentration of solid will be constant throughout the reaction. That's why kita assume dia sebagai satu. The activities of solid will be satu. Okay, tapi in terms of expression, it will not be included. Nampak tak? Dia tidak akan dimasukkan dalam tu sebab kita straight away kita letak satu dekat situ. Okay, kita letak satu. So that's why there's no concentration of sodium carbonate and sodium hydrogen carbonate. Okay, alright. So Kp dia akan referring, like I said, pressure. There's no pressure for solid. Solid tak ada pressure. Okay, gas sahaja yang ada pressure. So, siapakah gas dalam kes ni? H2O dengan CO2. So, that's why ada PH2O dengan PCO2 saja. Aqueous tak ada in case tiba-tiba ada aqueous kat sini, so aqueous will not be included in this expression. So kebetulan dua-dua yang tinggal tu adalah gas. So sama, dia macam sama dengan KC dia. Tapi not necessarily be the same dia depends. Ingat pressure kita go for gas sahaja. Kalau tiba-tiba dekat sini ada aqueous, so it will not be included in KP but will be included in KC. Okay? Alright, look at second example here, guys. Okay, so kita ada aqueous, we have liquid, and then aqueous. So this is another mixture of phases. Okay, phase. So we have more than one phase exists in the reaction mixture. Okay, how do we write Kc? Okay, how do we write Kc? Kc, that means kita consider for aqueous. Even though it is aqueous, it is still it will still have concentration. Aqueous kan? Aqueous tak ada concentration. Liquid, do we have concentration for liquid? Pure liquid? No, we don't have concentration for pure liquid. Sama juga, it will always be constant. So solid and liquid will not be expressed in Kc. Okay, tambah kat situ sikit. Will not be expressed in Kc. Okay, alright. Yang kita include kan yang aqueous sahaja. Aqueous. So, how do we write the Kc? Sama. Product over reactant. Power dia refer kepada coefficient. So, we only have CH3CO minus because this is the product times H3O plus divided by CH3COOH. Do not include H2O because it is in liquid form. And how about Kp? Do we have Kp for this reaction? No, we don't. Kenapa? We don't have gas in this reaction. Tak ada satu pun yang gas. Kalau ada satu gas, boleh. Boleh, maksudnya we still have Kp. But we don't have any gas produced or involved as reactant in this reaction. Therefore, we don't have Kp at all for this one. Okay? Tak semestinya dia kena ada Kc dan Kp. Not necessarily. Refer to the reaction. Do we have what do we call that? Do we have gas involved in the reaction as product or reactant? If we don't have any gas involved, that means we don't have Kp lah. Okay, we cannot measure Kp. Okay? Okay. This one yang saya mention tadi, yang solid tadi. Okay, for any pure liquid. So you may be wondering tadi kan, kenapa liquid tak masuk? Kenapa solid tak masuk? Tapi saya dah beritahu kan, it's because of the concentration remain constant. Okay, the concentration remain constant. Okay, concentration dia tak berubah. This is only provided for pure solid and pure liquid. Contohnya H2O kan, it must be pure water lah. Maksudnya pure ni tak ada campuran ada substance in the water. Okay, kalau ada campuran that means ada concentration lah kan. So kalau there's only H2O molecules in the container, so that is considered as pure water. So pure water, concentration dia macam, how do we measure the concentration? Kan? Because it's pure, dia substance yang pure. Dia 100% water. Okay? So dia punya concentration dia tu constant lah throughout. Maksudnya as long as there's no other substance in the water, that means the concentration of water, the purity of water. So usually we don't use concentration, we use purity lah. Okay, so the purity of water is 100%. So concentration kita assume dia constant. Same goes to solid. Okay, at constant temperature, the concentration is constant. Therefore, the concentration of pure solid and pure liquids are not included in the equilibrium expression. Okay, like this one just now, tadi kan dia solid. Okay, tapi you have to consider, you jangan main simply jadikan dia kosong. Don't do that. You assume that it is equal to 1. Okay, sama dia punya konsep dia product over reactant. This is product kan, so patutnya dia dekat sini. And then this is reactant. So you have sodium hydrogen carbonate. Ikutkan. Tapi since dia equal to 1, so kita tak ni lah. So dia sebenarnya 1 dia. Okay, the activity of pure solid is equal to 1. Okay, so the reason why solid lah. Okay, liquid kita dah faham. Dia kalau dia pure, purity dia 100%, we don't have concentration to describe liquid because it is 100% pure. Okay, alright. So how about solid? How do you measure the concentration of solid? Can we measure the concentration of solid? Yes, we can measure the concentration of solid. Boleh measure the concentration of solid. Okay, it's just that the concentration of solid tu dia constant. Contoh lah, okay, contoh. We are talking about sodium hydrogen carbonate. This is 1 mole of sodium hydrogen carbonate. And this is the volume of sodium hydrogen carbonate, of 1 mole of sodium hydrogen carbonate. So to get concentration, mole divided by volume. Betul tak? Sama saja. Mole divided by volume. So we got this one. This is for 1 mole. Okay, if you were to calculate for 2 mole of sodium hydrogen carbonate, you calculate 2 mole, and this is the volume, okay, volume of sodium carbonate. As you can see, bila the mole increases, the volume also increases. And then when you try to calculate the concentration, see, you will still get the same concentration there. Tak ada masalah, boleh calculate concentration. It's just that bila you calculate, kalau dia kecil, that means dia still proportionate dengan volume dia. 1 mole, so volume dia kecil lah. Tapi kalau we have 2 mole, the volume increases, betul tak? But when you calculate the concentration, the concentration is still the same. Sebab bila dia punya mole increases, volume dia pun bertambah. Lainlah kalau mole dia increase, volume tak bertambah. So that means concentration will be different. But this time, not only the mole increases, the volume also increases. So that's why they end up with the same value of concentration. Value dia tetap sama. So that's why kita kata concentration for solid is constant. Okay? So that's the reason why we said solid has a constant concentration. Okay? Okay guys, question checkpoint 2, write the equilibrium expression for Kc and Kp for the following reaction. Okay, I give you like maybe 3 minutes for you to complete all A until D. Okay, do it now. Try first. Okay, we'll discuss after this. Ish. Okay, are you done, guys?
Yes.
Okay.
Yes.
Right. Okay. Very
Yes.
good. You just have to write the equilibrium expression Kc and Kp only. Okay. There's no calculation involved. At least not yet. Okay. Jom, let's look at the answer. Okay. So that is for A. Okay. Please check with your answer. Is there any correction? Please let me know so that I can do the correction right away. Okay, please check sama tak sebiji dengan jawapan yang awak dapat. Any question, please let me know ataupun any pembetulan. Okay. Lupa equilibrium constant. So how is it? Is it the same for all?
Yeah.
Okay. Sama
Yes.
Okay, very good. So look at C. Question C. This one, okay, because we have 1 over concentration and this one 1 over partial pressure, kan? Okay, let's look at C. Okay, so we have solid here and we have liquid there as product, but we have gas also. Okay, so remember this one kita boleh replace sebagai 1 lah. Okay, dia punya concentration ataupun the activities is equal to 1. So Kc would be, kalau everything is there, it should be P. Kita terus, sebab dia liquid kan, is either you boleh buat macam ni, 1 per, sebab dia the only product that we have. Okay, and then dia liquid, so it will be 1. Okay, kalau dia gas, that means you kena tulis lah PCl3 raised to the power of 4. This one is liquid, so dia 1 lah. Divided by, so we have Cl2 kan tadi, Cl2 to the power of 6 lah, sebab dia punya ni kan. And then how about P? P is solid, so sebenarnya dia 1 juga dekat situ. Nampak dia solid, terus dia 1. So kita simplify, it will be Cl2 kuasa 6. Jangan jadi macam, jangan you simplify jadi begini Don't. Ini mana sama? Ini dengan ini tidak sama. 1 per dengan CL kuasa 2 per kuasa 6 is not the same. Okay, CL kuasa 2 per 6 ni dia per 1. Ni dah terbalik. So that's why dia tidak begini. Okay, alright. Okay, D we don't have KP for D. We don't have KP for D, but we do have KC. Okay, alright, good. Okay, now we are going to calculate the value of Kc or Kp given the concentration of partial pressure of all species at equilibrium. So kita nak apply the concentration. Just now you just express in terms of concentration lah. Okay, now we want to calculate the value of Kc. The numerical value, nombor dekat situ. Okay, alright. So we're going to start applying values now. Okay, alright. So let's look at example. Methanol is produced commercially by catalyzed reaction of carbon monoxide and hydrogen. So this is the reaction. Okay, alright. At equilibrium, an equilibrium mixture. Ini statement yang menunjukkan that at that time is already at equilibrium. Remember tadi kan saya kata you have to confirm yang the value given tu is at equilibrium, then only you can calculate for Kc. Because this means equilibrium constant. Kalau you yang dibagi value tu is not at equilibrium, mana boleh masuk dalam KC? Ikutkan by right. Okay? Alright, so you have to confirm. How do you confirm? So you have to look for this term, okay, equilibrium mixture ataupun at equilibrium. So it shows that the value given are at equilibrium. Okay? Alright, so at equilibrium, 2 liter vessel is found to contain 0.04 406 for methanol, which is the product, and then we have CO, and then H2. Okay, so as you can see, we don't have liquid, we don't have solid. Okay, so all will be included in the Kc. Calculate Kc at this temperature. Okay, alright, as you can see, dia bagi dalam mol. Dia tak directly given in terms of concentration. So maksudnya you have an extra work that you have to do first before you can insert into Kc, because Kc need to be in concentration. Okay, it need to be in concentration. Okay, so masukkanlah. First you have to have this, guys. Okay, you have to make sure that your Kc expression is correct. So imagine if your Kc expression is wrong, your value will be wrong as well. So be careful on the power ni. Be careful, don't miss out. Okay, because if your Kc or Kp expression is out, maksudnya is wrong, definitely your value will be wrong as well. Definitely. Potong jari lah. Okay, so that's why you have to, first step is you have to learn the correct way to write the expression. Okay, alright, so try out checkpoint 3. Do we have other checkpoint? Do we have checkpoint 4? Yes, okay, 2 checkpoint. Okay, guys, please complete these 2 checkpoint first, and we will discuss it after this. Okay, I give you like maybe 5 minutes. Okay, 5 minutes for you to complete these 2 checkpoint. Okay, go through it first and then try to solve it. I need to go to the toilet. Okay, we'll come back after this. Alright, so let's discuss. Answer. Okay, alright. Question 1, the equilibrium, checkpoint 3. Okay, the equilibrium of this reaction is established at 500K. So the equilibrium, okay, is established at 500K. And the equilibrium mixture of the gases has partial pressure of this. Okay, for all of the reactant and product, calculate Kp for this reaction at 500K. Okay, alright. So this is a very straightforward question. The question needs you to calculate Kp, and then as you can see, all the pressures are given and already mentioned at equilibrium. Okay, alright. First thing first, you have to write your Kp expression correctly first. Okay, and then you insert the values, and finally calculate the final Kp. Okay, alright. So this would be your how you should write your Kp. Okay, kenapa macam ni? Okay, sepatutnya tak beginilah. It shouldn't be like this. Sepatutnya dia begini. Okay, alright. So dia ada power kan? PNO is also power of 2. Yep, that one. Sebenarnya ni dekat luar ni, dia begini. Okay, alright. So you have to have the pressure there. If you don't have pressure, you ada NOCl macam tu sahaja, that is wrong. Apa ni bracket ni menunjukkan apa? NOCl apa? Mass, volume, pressure, concentration, apa? Okay, so that's why you have to have P. Tapi concentration is not a problem because dia bila dia square, it shows that dia concentration. Tapi concentration siapa? NOCl, for example. Okay, alright. So this is the final value of Kp. So don't bother to write any units for Kp and Kc. Okay, guys? Okay, that is checkpoint 3. Question 4, checkpoint 4, question 1. The equilibrium constant Kp for the decomposition of phosphorus pentachloride to phosphorus trichloride and molecular chlorine is found to be 1.05. This is Kp. That means this value is obtained when the system reach equilibrium, at equilibrium, because we are talking about equilibrium constant. Okay, so this is the Kp, the value of Kp. If the equilibrium partial pressure PCl5, PCl3 are this, what is the equilibrium partial pressure of Cl2 at 250 degree Celsius? Dia cakap juga dekat sini, equilibrium partial pressure. That means kita boleh equatekan all these is equal to Kp. Because this is at equilibrium kan? Kp confirm lah. The value of Kp is the value at equilibrium. So dia beritahu dekat sini equilibrium partial pressure. That means kita boleh equatekan all this punya partial pressure will be equal to Kp, which also equal to 1.05. Okay, alright. So dia nak cari. Okay, first thing first, you have to have your expression. Okay, as you can see, all the coefficients are 1. Okay, all the coefficients are 1. And then betul, okay, baru you masukkan. So you want to find out the partial pressure for Cl2. Okay, so this is mathematics. Okay, expression sini saja yang you akan buat. This is the chemistry part. So the rest are all mathematics. Kalau salah kira, so tak boleh bantulah. Salah tekan calculator, itu pun tak boleh nak tolong. Okay, alright, moving on. Any questions so far before we proceed? Okay, tak ada Okay, let's proceed. The magnitude of equilibrium constant. Okay, so how do we translate ataupun how do we explain from the value of Kc? What does the value of Kc means? You ada value tadi kan, 50.0. What does that mean? Apa maksudnya 50? And then you ada value pula 0.5. In comparison tadi 50 and 0.5. Apa maksud dia? Kena must be able to explain lah. Okay? So dia bukan sekadar you kena kira saja. You kena tahu how do you describe the Kc. How do you describe in terms of product? How do you describe in terms of reaction punya rate? Kan kita kena, kan kita tahu equilibrium when the forward reaction is equal to reverse reaction. Okay? Alright. So how do we how do we relate in terms of concentration of product, concentration of reactant based on the Kc value just now. Okay, dia tidaklah sekadar value je, senanglah kita nak calculate. Tapi kita must be able to explain it. Okay. Apa maksud dia? Okay. The size of Kc, the size means the value of Kc lah. The size of Kc give a measure of how far a reaction proceeds towards product at a given temperature when equilibrium is attained. Okay. So it is a description. Kc is actually a description of how far a reaction proceeds toward product. Dia pergi ke kanan. Dia suka tak pergi kanan? Atau dia suka pergi kiri ke? Okay. Dia suka produce product tak tadi? Based on the Kc punya value. Because you know Kc is equal to product over reactant, right? So kita boleh play around kat sini. Okay, kita boleh play around from this value. Okay, if the reactant at equilibrium, you can imagine at equilibrium kan, kita measure the concentration, we measure the pressure and whatnot kan. What if the reactant yang you measure tu, because at equilibrium, the concentration of reactant is higher than the concentration of product. So what will happen to this value? This value will be smaller, betul tak? Betul. This value will be smaller. So how do we describe this? So at equilibrium, the concentration of reactant is higher. Okay? That's why the value of Kc is lower. Contoh. Okay, we will look into that in detail after this. Okay, so that is what I meant by how do we describe the description of Kc from the value? How do we describe it? Okay, in terms of concentration of reactant, product and whatnot. Okay, alright. Kita ada 3 description for Kc. If Kc is less than 1, if Kc equal to 1, Kc more than 1, larger than 1. Okay, alright. So these are the 3 conditions that we need to consider lah. Okay, imagine you calculate the Kc values and then you found out that the Kc, the value of Kc is very small, 10 kuasa negatif 6 for example. So apa maksud dia kalau Kc is very small? Okay, alright. So like I said just now, we know that Kc is equal to product over reactant. Okay, Kc is equal to product over reactant. Okay, how do we, okay, let's go for the first one first. How do we get Kc less than 1? How do we get Kc less than 1 based on the product over reactant kat sini? Value apa yang kena lebih besar in order to get Kc less than 1, guys? Reactant. Okay, in order to get Kc less than 1, okay, macam mana nak dapatkan less than 1? This value kena besar ataupun this value is way smaller, kecil. Okay, bila you bahagi, you tekanlah any values, tekan kat calculator tu. Kalau this value dekat bawah, the denominator is larger, definitely larger than the product lah, the larger than the denominator kat atas ni, definitely this value will be smaller. Maksudnya reactant dia, okay, you kena imagine okay, so value, this is mathematics. Okay, reactant punya value lebih besar daripada the product, that means the value of Kc will be smaller. Okay, so imagine now for a reaction at equilibrium. Maksudnya dia dah establish, the equilibrium has been established now. Okay, so pada ketika itu, you boleh imagine, oh dah establish lah. Tapi at equilibrium, the concentration of reactant is higher than the concentration of product. Walaupun dia dah reach equilibrium, that's why saya kata concentration tak semestinya kena sama kan. Concentration remain unchanged, tiada perubahan, but not necessarily be the same. So reactant punya concentration is higher than the concentration of product at equilibrium. Sebab reaction ni ada nature dia sendiri. Dia tak semestinya produk tu kena banyak, not necessarily. Ada reaction yang produk dia sikit. Okay, contohnya kita nak produce drug. Drug is very hard to produce lah. Even the percentage of drug produced is, I would say, rather small lah compared to other simple reaction, other reactions. Because drug is, dia punya proses tu, dia punya pathway tu is very complex. Tapi we want the drug That's the only way. Kita dapat percentage yield dia dalam 40%. Maksudnya 40% of product produce. Okay, so kita boleh imagine that at the end of the reaction, contohlah, katakanlah dia involve equilibrium. At the end of the reaction, there's still a lot of reactant present in the reaction. But we do have product in small amount. So we have to make use of it lah. Because that's the only way so far that we can produce that particular drug. Contoh. Okay, so this one, after the reaction has achieved equilibrium, we have identified that the reactant punya concentration is larger than the concentration of product. That's why lah KC dia dapat less than 1. Okay, maksudnya dekat sini, extremely small amount of product are formed. Like I said, product very low. The position of equilibrium, when we are talking about product, maksudnya product is very low. Product very low sebab reactant banyak lagi kan. Walaupun dah reach equilibrium. Okay, we are talking at equilibrium because kita cakap pasal KC now. That means the reaction, the position of equilibrium lies strongly towards the reactant. Remember yang arrow forward dengan reverse tu kan? Okay, so dia produce product, but the equilibrium position dia favors to the left, which is producing more reactant. That's why reactant become higher. The concentration of reactant become higher. Okay, faham? Itu dia punya translation dia tu. Maksudnya soalan favorite dia adalah the position of equilibrium. You must be able to describe in terms of position at equilibrium. The product is small. Kenapa dia punya concentration of product is smaller? Because the position of equilibrium, direction of equilibrium is favoring to the left. Left maksudnya dia suka pergi dekat reactant. Dia produce more reactant instead of pergi ke kanan. Okay? Faham tak? Kalau you faham yang tu, then KC is equal to 1. KC is more than 1. You patut faham lah kalau you faham this concept. Okay? Alright. So, KC is equal to 1. Okay guys. KC is equal to 1. Product over reactant. Sama. Kita pakai product over reactant. How do we get KC is equal to 1? Bila product and reactant are more or less the same. Sama ataupun more or less the same lah. Okay. Alright. So, kalau 10, 20 tu kita consider dia lebih kurang sama lah. Kat situ Tapi dia still product is higher than reactant. Okay. So, equal to 1. Maksudnya dia punya concentration of product and concentration of reactant at equilibrium are almost the same. That's why value dia kita boleh dapat 1. Katalah sini 50, sini 50. So you get 1. Betul tak? Okay. So apa maksud dia? What does that represent? Apa maksud this one? Maksudnya at equilibrium, okay, the concentration of product and the concentration of reactant are almost the same. Okay, so how about the position of equilibrium? Position of equilibrium dia tu sama lah. Okay, the rate of forward and the rate of reverse reaction are the same. Okay, see, baca dia punya statement. The concentration of reactant and product are similar at equilibrium. The position of equilibrium lies approximately midway, maksudnya dia tengah-tengah between reactant and product. Dia tak favor macam yang this one tadi, dia favor to the left, producing more reactant. Okay, that's why lah value dia dapat less than 1. Okay, but this one, dia tak favor mana-mana, dia tak bias, dia lebih kurang sana, midway, dia tengah-tengah. Produce reactant, produce product. Okay, alright, so KC is more than 1 guys. KC is way larger than 1. Sama juga. Okay, product KC is equal to product over reactant. So how do we get KC more than 1? That means the value of reactant is very low, but the concentration of product is very, very, very high. That's the only way for you to get the value of KC more than 1. Okay, mathematically lah value dia. Okay, how do we describe in terms of position of equilibrium? Maksudnya, at equilibrium, kita akan dapat banyak concentration of product. The concentration of product is very high. So, how about the equilibrium position? Maksudnya, at equilibrium tu, in order to achieve equilibrium, the forward reaction, forward maksudnya pergi ke kanan to produce product kan, sebab produk tinggi kan, okay, lebih dia favor the forward reaction ataupun rate forward, okay, is faster than the rate reverse. That's why dia boleh produce banyak produk and eventually dia sama kan, because nak reach equilibrium dia kena sama. Eventually dia sama. So when the equilibrium has established, kita measure, oh produk banyak, reactant sikit. That's why dia kata, the position of equilibrium lies strongly towards the product ataupun dia favor going to the right. Okay? Alright, faham tak everyone? Okay ke?
Okay.
Okay.
Yeah. Alright. So you kena faham that one because ada soalan dia akan tanyalah, maksudnya explain ke apa kan later on. So that will be based on the description of the KC just now. Okay, we have 3 possible condition for KC. So based on the value of KC that you have calculated. Okay, cuba tengok question 1. Okay, ini boleh kita determine directly, okay? Based on the value that we have that is given to us. Identify the reaction that lies to the right. Maksudnya yang favor pergi ke kanan. Bila dia favor, maksudnya the forward reaction. Kanan forward kan? Forward reaction. It will produce more product kan? And what happened to the value of KC? The value of KC will be increased kan? Lies to the right, favoring the formation of product, and the reaction that lies to the left, favoring the formation of reactant. Okay, alright, kita kena identify. Okay, A. Okay, A alright, so based on the KP given. Okay, so how do we know whether it lies to the right, the equilibrium position lies to the right ataupun lies to the left? Dia favor, okay, jawab soalan pertama dulu. Ni lies to the right ke ataupun to the left based on this value? Guys.
To the right.
Right.
Okay. Alright, very good. How about others? Baru 2 orang aja yang cakap, 46
Right.
orang ada dalam tu.
Right.
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 Okay.
Kanan. Right.
Okay, very good, to the right. And then dia favor product ke dia favor reactant for A ni? Question number 2.
Product.
Product.
Okay.
Product.
Thank you for the response. Dah pergi ke kanan kan? Maksudnya pergi kanan buat apa? Produce product. Sebab dia 2 soalan kat sini. You baca betul-betul Dia tanya equilibrium position and then dia tanya to the left favor product and the reaction that lies to the okay. Dia tanya satu je soalan. Cuma kita kena describe in terms of position of equilibrium and also the formation of reactant or product. Okay, alright. So A, the answer would be lies to the right, favor product. Okay, yang ni obvious lah. Ada 10 kuasa negatif 18. That is, the value will be very, very small. Okay, negatif 18, 0.0000018 kali 5.8. Okay, very, very small. Maksudnya sangat tak favor product. Reactant, dia sangat, you kalau confuse, you pergi buat macam ni, buat formula tu, product over reactant. Macam mana nak dapatkan value dia very small? This value very small, that means the reactant will be higher. So at equilibrium, the concentration of reactant is very, very high. Maksudnya tak suka produce product. Okay, maksudnya the reaction lies to the left. Dia produce more reactant ataupun at equilibrium, reactant lagi banyak daripada produk. Okay, so dia favor to the left sebenarnya instead of to the right. Dia favor reactant. Okay? Okay, alright. Kita dah lambat sangat sebenarnya ni. Sangat kita ni. Okay, patutnya minggu ni kita kena habis kita punya topik 2 je. Topik 2 habis minggu ni 2 minggu je. Next week topik 3 will be one of the challenging topic for semester 2 lah. Okay, stand by. Okay, relationship between Kc and Kp, we can relate Kc and Kp. So this is normally applicable to gas mixture, guys. Okay, for a gas mixture, so the relationship between Kc and Kp can be represented as Kp is equal to Kc RT delta N. Okay, alright. Your first formula, guys, for topic 2, Kp bukan Kc Kp is equal to Kc times RT, okay, both in bracket, raised to a power of delta N. Delta N. So what is delta N? We will look at into that later. Okay, if we have example, even better lah. Okay, kalau here, okay, this formula is actually derived from, nampak tak macam ada arti-arti kan? Dia sebenarnya derive daripada gas law, daripada ideal gas equation. Whoever interested in knowing in detail ataupun nak derive, you may look into this, okay, on the internet, in the textbooks, okay. Nak tahu macam mana finally they end up with this one. Last time we do have a slide on this, but that one is just to show you on how the formula is finally derived. Tapi kita tak tanya pun dalam exam. Okay, that's why we discard the slide ataupun kita remove the slide. So anyone, any student who like to know in detail, you may go look for it. Okay, tapi saya bagi, dia punya overview dia, bukan overview, dia punya idea dia adalah it is derived from the ideal gas law, ideal gas equation. Okay, they rearrange this one. Okay, and finally end up with this one. Saya macam biasa, saya dah try, so saya dah tahu, so saya dah cukup puas hatilah. Okay, then we are running out of time, so saya tak ada, memang kita tak sempat untuk nak tunjuk. Okay, right, so delta N, what is delta N? Moles of gas product minus the mole of gas reactant. Okay, alright, so the R used will be 0.0821. This is the unit. dm3 ataupun liter lah. Usually we use liter kan. dm cube, alah, gantilah guna liter lah. Tapi take note juga liter is also equal to dm cube. Okay, liter ATM K negative 1, mole negative 1. Okay, so don't get confused. Okay, topic 1 last time we used 8.314 kan, because it involved energy, but this one it does not involve energy. That's why we use this value of constant. Okay, alright, so the relationship of Kc and Kp can be derived by using ideal gas law, PV and RT. So this is a formula, guys. Do not get confused. Jangan pergi letak Kc, Kp. No, it's not the same. Okay, ini salah. It should be Kp is equal to Kc RT delta N. Okay. Tiba dia tercarry forward. Okay, look at example. Okay, look at example. Calculate the value of Kc for the following reaction given Kp is equal to this. Okay. Alright, so this is the equation. So Kp is already given. Dia suruh you calculate for Kc. Okay, alright. So Kp dah bagi, R is not a problem, T also is not a problem because it's already given in term. It's already given, but you have to convert into Kelvin. Okay, guys, please be careful. You have to convert into Kelvin. Now, how do you calculate delta N? Okay, alright. So you have to consider for gas only. Okay, gas sahaja. Aqueous tak termasuk, ya. Yeah? Alright, okay. So this one you kena totalkan reactant 2 plus 1. Make sure yang gas dulu, gas sahaja. So 2 plus 1 will be 3. Okay, and then this one we have 2. This is product. Okay, so delta N is equal to N of product minus N of reactant. That will be delta N. Okay, so 2 minus 3 will be negative 1. Jangan ingat negative 1 tak boleh jadi dia punya kuasa, boleh. Okay, alright, so it will be negative 1. So tekan calculator, masukkan, make sure you got the right answer lah. Okay, provided everything is all correctly insert. Okay, alright, so ini tak ada masalah. Saya rasa ini mudah. Tapi kalau dia involve solid, dalam ni tiba-tiba ada solid kan? Macam mana? Bila solid, dia bukan satu tau. Koefisien dia bukan satu, koefisien dia kosong. So jangan confuse dengan concentration tadi, yang KC expression tadi. Do not get confused with that. Bila dia ada solid, imagine you have solid kan. Macam mana nak buat? A, 2A, contoh, this is just contoh. This is solid plus B, gas, C is also solid. This one 3C lah contoh. Okay, so how do you calculate delta N for this one? Delta N is equal to product tolak reactant kan? Okay, so dia punya product, this one will be 0. Okay, sebab any value, katakanlah concentration of the reactant, remember tadi kan saya kata concentration of solid will be equal to 1 kan? Sebab dia constant, kita assume dia sebagai 1 kan? So imagine kalau katakanlah any concentration, kita kuasakan dia kosong, kita akan dapat apa? 1 juga, betul tak? So that's why dia punya, kita bukan ambil 1 kita ambil kosong. Mol dia tu. Okay, mol dia tu kosong. Jangan confuse dengan KC yang awal-awal untuk solid tadi. Kosong, this one 1, this one kosong. Bukan 2. 2 memang bukan sebab dia solid ni. Okay, so dia punya mol dia kosong. So macam mana you nak tolak? Kosong, tolak 1 tambah kosong. So you dapat apa? Negatif 1. Okay, masalah student adalah delta N untuk solid dia pergi letak 1. Yang teruk lagi dia 3. 3 memang salah lah kan. Solid dengan liquid ni dia special, okay? So you kena mathematically dia kena macam mana kita nak dapat concentration dia 1. Kan kita kata concentration dia tetap dia fix 1. Kita kuasakan dengan kosong kan. That's why lah bila nak cari delta N which is the kuasa, kita letak dia sebagai kosong. Kita bukan letak dia sebagai 3, no. Kita bukan letak dia sebagai 1, no. Okay, kita letak dia sebagai kosong. Okay? Alright. Ada contoh nanti dekat dalam. So we have checkpoint 6. In the synthesis of ammonia from nitrogen and hydrogen, determine the value of Kp. Okay, what is the time now? So we are running out of time. Okay, alright. This one you can try out on your own. We will discuss it tomorrow. Okay, try dulu. Okay. Manipulating equilibrium constant expression, guys. Okay. Okay. We can manipulate the equilibrium constant expression. Okay, so when the direction of an equation is reversed, the new equilibrium constant is the reciprocal of the original. Okay, all right. So we can manipulate from the Kc, the original Kc, in order to get the new Kc without having to maybe perform a reaction. Okay, katakanlah we have limited time. Okay, we don't have time lah. So basically kan nak perform a reaction, we can predict. Okay, we can predict the new Kc from the old Kc. Okay, contoh lah. So this is the original reaction. PCl3 plus Cl2 producing PCl5. So this is the Kc expression with respect to this reaction just now. Kc expression. So this is how we write. Okay, katakanlah kan kita nak calculate the Kc for the reverse reaction. How do we determine the value of Kc for the reverse reaction? Okay, alright. So we have alternative to this other than to perform the reaction itself, or we can simply derive from the old Kc, the original lah. So this is the original Kc kan, the original Kc. Okay, sebab dia basically they are all the same. It's just that the position of reactant and product are now opposite ataupun reverse. Okay, alright. So if we were to write the Kc of the reverse reaction, this is how we write it. Betul tak? Kita apa ni? Belum. Dia dah terlajak. Okay, sorry. We are talking about reverse kan ni sekarang ni kan. Macam mana boleh terlajak kat sini? Okay. Alright, so it's actually the same. It's just that they're being reversed. This Second, this is first, this is second. The second is a reverse of first reaction. So when we try to express the Kc from the second reaction, okay, this is how it looks like. Dia terbalik position dia saja, terbalik. Nampak tak? This is the original, this is the new one. So macam mana kita nak manipulate this one? So apa kita buat adalah, the Kc of the new one, the Kc prime ni is equal to 1 over Kc. You can simply calculate the value of the new Kc. Okay, tak perlulah susah-susah kita nak masukkan concentration dia. We can just simply calculate from the old Kc punya value. Sebab dia ada kena-mengena. It's just that dia punya position dia saja berubah tempat. Nampak tak? So, kita boleh satu perkan Kc tu. Bila kita perkan something, when we transfer back, kita transfer naikkan dia ke atas, kan dia punya position tu, dia jadi terbalik. Kan? Bila ni naik ke atas, dah lah dia ni per kan? The ratio. So, bila naikkan ke atas, kita akan terbalikkan dia kan? So, kita boleh calculate the new Kc without having to add in, to insert the concentration. This is what we call manipulating. Kita boleh manipulate. Okay? So, kita boleh conclude that the K reverse is equal to 1 over the K forward. This is the forward reaction, this is the reverse reaction. So how do we relate these two? So we can conclude that the K reverse ataupun the Kc prime, this is the Kc prime ataupun the K reverse is equal to 1 over K forward. Okay? Alright, so this is one of the way to manipulate, to use the original Kc, okay, in order to get the new Kc, provided dia punya reaction tu lebih kurang sama. Janganlah tak ada kena-mengena, macam mana you nak manipulate this one pula. Okay? Okay, other than reversing the equation, we can also manipulate the equation by kita ubah the coefficient. Ini macam Hess law last time. Kita belajar Hess law tu yang anything yang kita ubah on the equation, we must make sure that we alter the delta H. Remember last time? So it's actually the same understanding lah. Okay. Alright, when multiplying the stoichiometric coefficient of reaction, the equilibrium constant is raised to a power equal to that factor. Okay, ini kalau kita ada factor kat situ. Okay, this is the original and this is the new one. As you can see, it's actually the same. It's just that dia punya coefficient je sekarang ni. The first one is 1:1 ratio. The second one is 2:2 ratio. Okay, so this is the Kc original punya expression. This is the new one. So how do we relate these two? Dia benda yang sama dalam tu, benda yang sama kan? It's just that dia dua macam tu. So from there we can relate. Okay, Kc of the new one is equal to Kc kuasa 2. Sebab dia punya apa nama tu coefficient involved is 2. Okay, itu kalau 2. Habis kalau 3, 4, 5. So we can conclude that the K new yang kita nak cari tu, yang baru tu is equal to the original raised to a power of n depending on the coefficient that we have in the new equation. Okay, kalau dia 1/2 pun boleh kita 1/2 di situ. Okay? Alright, moving on. Ini senang lah. This is straightforward. So you have to remember this one. Okay, this is how you can manipulate lah. So without having to insert the concentration back into the new Kc and then tekan calculator, you boleh simply kuasakan saja the old Kc, the original Kc to get the new Kc. Okay, alright. Last but not least will be this one. When chemical equilibria are added, their equilibrium constant are multiplied. Okay, this is complex sikit. Dia taklah kompleks mana. It's because it involve more than 2 reaction. Okay, alright. So this is the first reaction. This is the second reaction. The first reaction, second reaction, and what we want is the third reaction. Ini macam Hess law. Okay, what we want is the third reaction. When we look at the third reaction, it's actually the combination of the first and also second reaction. Okay, the combination of the first and second reaction. Baru kita dapat this one. Sebab ni cancel. So you end up dapat 2N2. Okay, O2 ni total dapat 4O2 and then 4NO2. This is the intermediate kan. So what we want is the third reaction. This one is given to us. Okay, alright. So how do we calculate this new Kc? Kc new ni, how do we calculate that? How do we use the information from the two original Kc, Kc1, Kc2, reaction 1, reaction 2, so that we can calculate for the new Kc. Okay, alright. So this is the expression for the first reaction, Kc for the first reaction. Tulis as it, you express as it is. Okay, kuasa 2 apa semua product overrated. This is for the second equation, for second reaction. As it is for 3, 2, you can extract the kuasa from the coefficient in the equation. Okay, alright. Like I said, this final equation is a combination of these two kan. Okay, so how do we get? Dia sebenarnya komponen dia tu ada dalam nombor 1 dan nombor 2. Okay, alright. So the third Kc ni, the new Kc ni, kalau we were to write the Kc, kan cuba kita try write Kc untuk new ni. NO2 kuasa 4, N2 kuasa 2, O2 kuasa 4. Betul tak? This is the new Kc kan? Okay. How do we, this is the new Kc expression, but how do we manipulate these two in order to get this one? This new one. Okay, you darabkan dia. Bila you darabkan dia, you cancel. Nampak tak? You dapat yang sama dengan the new one. See? You dapat yang sama. Sama tak this one? Yang ni yang kita translate directly from this one kan? But this one is the one that we manipulate the first and second reaction to get the third equation punya expression. See? Exactly the same. Just by manipulating these two Kc. Dapat tak ni? This is your Kc3. This is actually the same lah. So what can we conclude from that guys? We can conclude that we can multiply sebenarnya Kc1 multiply with Kc2 is equal to the new Kc. Okay, we can simply multiply this 2 Kc to get the new Kc. This is only applicable if we have been given more than 2 reactions in order to get the new equation. Okay, alright, moving on. Okay, pukul berapa sekarang ni? Oh, kita memang tak sempat. Okay, checkpoint 7. Okay, try to complete all of this checkpoint. Try dulu. Okay, we will discuss it tomorrow. Jawapan. Okay, try. Dia very straightforward je. Okay, try dulu. And then we have question 8. You can also try question 8. Okay, based on manipulation just now. Try question checkpoint 8. And then we have checkpoint 9. Cuba buat. Okay, checkpoint 9 ni kompleks sikit. Tapi try buat. It is very interesting. Kalau you dapat buat. Okay? Okay. Tapi saya dah tunjukkan tadi macam mana how would you solve for it. You manipulate. Okay? Dia what is given to you is this one. Tapi soalan nak yang ini. How do you manipulate this one in order to get this? Tapi this time around dia bagi concentration. Dia tak bagi Kc punya value. Dia bagi concentration. That means you have to insert to get the Kc punya value. Okay. Yang this one, dia tak bagi Kc. Dia tak bagi concentration tapi dia bagi Kc. You can just use the formula from the manipulation just now. Okay. Okay. Try do it on your own first. We will discuss it tomorrow. Okay, maybe an overview of QC. What is QC, guys? Very quickly, what is QC? Berapa? 2 minit lagi. Okay. Direction, quotient and the direction of change. Ini last week patutnya kena habis ni, quotient ni. Okay, next we have Q. Just now we have K, KC. Now we have Q. Q is what we call quotient. QC, QP is Q lah basically. Okay, equilibrium, at equilibrium just now we have K, KC, KP. But this one we have QC or QP. Okay, so what is QC and QP? And the direction of change. Okay, right. Dia punya key dia very simple. Remember, KC and KP just now, we calculate KC and KP. They must be at equilibrium. We have to confirm that concentration or the pressure must be at equilibrium. So QC is opposite to that, which is not necessarily at equilibrium. Itu sahaja. But how do we calculate QC? It's actually the same as how we calculate KC. Itu sahaja. Okay, sometimes kita tak tahu. Soalan tak bagi. Macam tadi kan obvious kan. Dia kata at equilibrium. So obviously that will be, we are calculating for KC. But sometimes question did not give us any information whether the reaction is already achieve equilibrium or not. So tak tahu. Bila tak tahu, tak confirm, we cannot use KC unless it is confirmed. But what we can use is QC or QP. Okay? Bila kita dalam keadaan kita tak confirm, ni dah equilibrium ke belum? So that one is QC. Not necessarily at equilibrium. Okay? So kalau you dah confirm it is at equilibrium, that means the QC is equal to KC. Okay? So basically QC is calculated to determine in which direction a reaction will proceed. So QC tu dia bagi kita indicator that reaction ni akan proceed ke mana? Ke kanan ke, pergi ke produk ke ataupun ke reactant. Okay, kalau belum at equilibrium, it give us an indication on the reaction will at that particular time dia favor apa. Okay, dia QC ni at that particular time. Is it at equilibrium or not? Okay, tu QC. Tapi KC confirm mesti at equilibrium. Tapi QC, is it? Tak confirm? QC. QC is calculated in the same manner as KC. Sama exactly. Formula yang sama, pakai power yang sama, gas, solid tak solid satu, apa benda semua, exactly the same. It's just that not necessarily at equilibrium. Okay? Alright, so if we were to use graph, you imagine kalau graph, okay, kalau graph, remember ni concentration versus time. So kat kawasan, this is the once the equilibrium has been established kan, based on dia punya graph dah stagnant ni kan. So we could say that this is already at equilibrium. Kata kalau dia tak beritahu that concentration tu at equilibrium ke tak kan. And then when we try to calculate the concentration and we find out the value is the same as K. So this is where Q is equal to K. We could say that the system is already at equilibrium. Okay? Alright. So yang ini obviously this is not at equilibrium sebab dia belum sampai equilibrium lagi. So we could say that the Q is not the same as KC. Belum. The Q can be the value can change. Dia tak semestinya satu value dia boleh sebab kita ukur at any time. Kita nak ukur kat sini. Ni pun QC, ini pun QC. Kita nak check dia dah reach equilibrium ke belum. Selagi dia tak reach, it's not the same as KC. That means it is QC. It's not KC. Okay? So ini based on this graph, kita tahu it's not yet at equilibrium. So QC will definitely not be the same as KC. But how do you write it? Exactly the same. Okay? Sama. This is for the how do you write the reaction quotient expression. Okay? So buat sendiri. Okay. Okay, so this is the indication. Okay, remember just now kita dah belajar direction for KC tadi kan. Kalau based on the value, apa yang kita boleh predict kan. So Kalau value dia besar, dia suka produk, KC just now. Kalau value dia very small, dia favors to the left ataupun favors reactant. Same goes to QC. Remember, QC is at that particular time, whether it's already equilibrium or not. Pada ketika tu, kita nak check. Okay, so that's the idea for QC lah. That one kita akan discuss in detail tomorrow. Okay, alright. So we have few more slides on this. Yang mana yang you boleh calculate for QC, you can calculate for QC. Okay, before we proceed to the next subtopic. Okay, alright. So that is all, guys, for today. Any question?
No.
Okay, if there is
No.
no question, I think that is all. Okay, so thank you everyone for your attention. Okay, alright. Assalamualaikum and bye. See you tomorrow.
Thank you, madam.
Thank you, madam.
Thank you,
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.